Here's going to be our more concrete description of automorphisms of the disk, again, which is fractional linear transformations that send the unit disk onto itself. So it's going to be very concrete. It's not going to be in terms of matrices. For any alpha in the unit disk, define this function m sub alpha of z, which is alpha minus z over 1 minus alpha bar z. And then our main theorem here is going to say that the automorphisms of the disk, when written in sort of the complex plane form, are going to be of this type. There'll be a constant mu on the unit circle times m alpha, where alpha varies over the unit disk. Let's see how to prove this. First, we have to prove some things about m alpha. The most interesting thing is that m alpha is its own inverse. So you plug m alpha into itself and you get the identity map. And we can also show that m alpha is an automorphism of the disk. So to show that m alpha is its own inverse, well, we can convert it to this matrix form, and the matrix associated to m alpha is this, because notice m alpha z was minus z plus alpha. I'm rearranging things to put them in the right form. On the bottom I have minus alpha bar z plus 1. So the coefficients are minus 1, alpha, minus alpha bar, and 1. And now I can compute the inverse of this within PSL2C, so I don't have to divide by determinants. So I'm just switching the diagonal entries and putting negatives in front of the off-diagonal entries. And we can multiply everything by minus 1 inside of PSL2C. And we get that this inverse matrix is equivalent to the following, which was our original matrix. So that shows that m alpha inverse is m alpha. So FA inverse is FA, or MA is its own inverse. So m alpha composed with m alpha is the identity. The next thing to show is that m alpha sends the disk onto the disk. And to prove that, we use this magic formula, which was a homework problem. 1 minus m alpha squared can be factored into this. And this shows directly that if z is less than 1 in modulus, then m alpha is less than 1 in modulus. So it sends the disk into the disk, and since it's its own inverse, you can apply m alpha to both sides to see that the disk is also inside m alpha of the disk. So this proves that m alpha is an automorphism of the disk, so everything of this form, mu times m alpha, is also an automorphism of the disk. The main thing now is to show the converse. So let's look at an FLT that sends the disk onto the disk. Again, a continuity argument similar to what we did with the upper half plane shows that it sends the unit circle into the unit circle. Let's write our FLT using a matrix, and we'll define little f mapping on just the complex numbers as we've done before. Now, just a quick observation. Notice that a complex number has modulus 1 if and only if it's equal to 1 over its conjugate. So if we take a complex number of modulus 1, then we're saying that FA of z has modulus 1. And so when you plug such a point into here, it equals 1 over its conjugate. That's what this expression is. But if z is on the unit circle, then we have this property, so I can multiply through the top and bottom by z to get that it's of this form. And this is actually equal to 1 over FA, let me write it first, it's equal to 1 over the conjugate of FA of 1 over the conjugate of z. And this holds on the unit circle, which is more than 3 points, so it has to hold everywhere. And this is also an FLT, so FA is equal to 1 over the conjugate of FA of 1 over z bar, so it has this reflection property. We only need this just for 1 point. If I define alpha to be the inverse image of 0, then what we get out of this is that 1 over alpha bar maps to infinity. And that lets us completely factor little f. The top has to have alpha as a 0, and it has to have 1 over alpha bar as a 0 at the bottom. So FA has to be a constant times this, which is just a constant times m alpha. The constant has to be 1 because, or has to have modulus 1, because this is already an automorphism of the disk. If the constant had larger modulus, you would map into a bigger disk. If it had smaller modulus, it would map into a smaller disk. So it has to have modulus 1. And so we get the theorem that FA has to be of the form mu m alpha, where mu is on the unit circle and alpha is in the disk.